All right, thank you very much. Today I'm going to be talking about analysis for answering arbitrary user queries over failure reports. This is work by myself and a number of co-authors, all at the University of Wisconsin in Madison. So suppose your software has crashed, and worse still, it crashed in production. Now you're left with a failure report that contains just scraps of information about what happened on the failing run. So you probably have a lot of questions about that run. For example, you might wonder, did the application call appropriate initialization routines? Did the application ever enter a privileged context? Could the application have locked a stream without later unlocking it during the failure? Or perhaps, what was I even thinking when I wrote this code? Well, okay, so this last one's gonna be out of scope for this work. But for the others, if we were running the application in-house, the questions are much easier to answer because the failure report probably contains a full execution trace. But for deployed applications, we can't gather a full trace because of time concerns, because we don't want to damage end user performance, memory concerns, and ideally we'd additionally use no extra disk space, and finally privacy concerns, because we don't want to gather extra user sensitive data. So because of this, production tracing tools will often leave just fragmentary clues or just partial data about the run. And this characterization applies to the vast majority of tools for tracing deployed applications. Now, many postmortem analysis techniques exist in the literature for tasks like execution replay, localizing faults, program slicing, and so on. However, debugging is all about asking and answering questions about runs that could possibly produce observed failure data. And this is the goal I'll focus on in this talk. So today I'll describe our analysis engine, CSI Grissom, which takes as input a program's control flow graph and a failure report that might contain information like log files, stack traces, and so on. The user can then ask any number of queries one at a time. So for example, a user might ask, did a particular statement in the program execute during the failing run? Grissom then answers whether the query is possible or impossible on any run consistent with the failure report data given. Thus, more failure report data will result in more precise results with respect to the actual failing run. Now, any solver I propose here that can more often answer impossible is going to be more precise. That is, if a solver can't be sure that a query is impossible, it must say possible. The general approach is going to be to encode languages for failures, such that strings represent paths through the program's control flow graph. So thus, the alphabet of these languages will be the nodes of the control flow graph. So if we think of each component of a failure report as constraints on paths through the graph, then we need to encode our control flow graph, encode the failure report, and encode the user's query in some formal language model, and strings in the resulting language, if we intersect all of these, represent paths through the graph consistent with the failure report and the user's query. We're interested in if this intersection is empty or not. So I'll fill in the details of this high-level idea as I go through the talk. I'm going to use a somewhat complex example today to highlight our handling of inter-procedural and stack-sensitive properties. The example has three functions. First, the main function with its control flow graph shown here. And note that these dotted edges represent calls and are labeled with the calling node subscripted by the called function. The second function is function foo, and its control flow graph is shown here. And note that these dashed lines are returns and are labeled for the call that they match to. The final function is bar, and it's a smaller function shown here. Next, let's look at some example failure report data for a run. We might get a stack trace, something like this. Perhaps we crashed at statement n in function bar, called from statement j in function foo, and so on. Perhaps a log message, and let's assume for this example that a static analysis can determine that processed could only be printed by statement B or statement C. Finally, the user provides a query. So for example, the user might ask, is it possible that statement E ever executed on this failing run? Note that for this particular example, a precise analysis that can express calling context should answer impossible given the crashing stack context. There's no recursion and no loops in this example, so we must have crashed before ever executing statement E. Now we investigate three solvers that trade off precision and scalability in this space. The first is based on symbolic visibly-pushdown automata, or S-VPAs. The second is based on finite-state automata, or FSAs. So here we give up calling context sensitivity in our encodings. And finally, unreliable trace languages, which is a new sub-regular language class that I'll introduce in this work. Note that one important element of a solver's precision is its expressiveness, or what types of failure report constraints we can express with that solver. I'll comment on this a bit as I go through the talk, but just note that we're going to require that all failure report elements and the user's query can be described in some appropriate formal language model for each solver. So I'll begin by talking about the S-VPA solver. Now, symbolic visibly-pushdown automata, like context-free languages, can recognize match parenthesis languages, that is, call and return sequences, but they also have many important properties of regular languages. Most notably, they're closed under intersection. And recall that our problem is one of language intersection, so this is an important property for us. Hence, with S-VPAs, we'll be able to encode our control flow graph context sensitively, and all failure report elements and the user's query must be definable as symbolic visibly-pushdown automata. Now, symbolic visibly-pushdown automata are different from standard finite-state automata in a number of ways, and I'll focus on just the important details for this talk. Here we see an internal transition, and these will represent intra-procedural flow in our encodings. Note that it takes a unary predicate over input symbol x. Here the predicate is x equals a, indicating we intra-procedurally execute statement A. Next, we see a call transition as indicated by the C. The true predicate indicates that we can read any symbol, and we push a 0 onto our automata stack. So for example, if we see a call on symbol B, as indicated by the open parentheses in the input string, then we would take this transition, pushing a 0 onto the automata stack, and noting that the symbol that we read was B. Finally, here's a return transition. It again pops a 0 off of the stack and takes a binary predicate, where X is the current input symbol we're reading, and Y is the call symbol that we're trying to match to. Here we assert both are equal to B. So in this case, the call transition pushed a top of stack symbol B. So if we see a return on B in our input string, as indicated by the closed parentheses, we can take this return transition and pop the top of stack symbol. Now, to encode the context-sensitive control flow graph, the basic idea is to introduce accepting states for each control flow graph node, indicating that from control flow alone, we can't know where we crashed. So rather than show the whole encoding, I'll just give a few examples. Intra-procedural flow is encoded via internal transitions labeled with the target of the control flow edge, while calls and returns are matched via the label at the call site, which again is the call node subscripted by the called function. Next, I want to talk about encoding crashing StackTrace context. Now, a general crash stack is a sequence of function call labels followed by a crash point. So for the StackTrace from our example, here's the thing that we want to encode. This sequence, and we want to encode it as a series of well-matched sequences of calls and returns separated by the calls that we expect to be left on the failing stack. So we need to first represent the sequence of calls and any amount of intra-procedural execution in between these calls, and well-matched sequences of calls and returns occurring outside of the failing stack. Now, the full encoding here is a bit messy, so I'm leaving out some details about how we encode well-matchedness. I'm more than happy to talk about this with you after the talk, or please see our paper for full details. Finally, we might want to encode program coverage data, perhaps as gathered by a tracing tool. Now, the general form here is a mapping from control flow graph nodes to whether each executed or not. So for an executed entry, it would look something like this, stating that we need to see an N1 node at least some point during the failing execution, while an unexecuted entry would say you can read any symbols you like, just never the unexecuted symbol N2. Now, our example query is actually all about program coverage as well. In particular, it's statement coverage at statement E. So its encoding is shown here on the slide. So at this point, I've described how to encode the control flow graph, failure report, and query as S-VPAs. So now we can use standard mechanisms for automata intersection emptiness in order to answer our question. If the intersection is non-empty, then there exists a context-sensitive path through the control flow graph that satisfies all failure report constraints and the user's query. So we answer possible. Otherwise, we answer impossible. Now this S-VPA solver is quite precise, as we'll see when I get to experiments, but it requires computing intersections over these automata, which can be quite an expensive operation. So the next solver I'll describe instead uses regular languages and finite state automata to trade off some of this precision and expressiveness for scalability. Here we have only internal transitions because there's no automata stack to manipulate. So all three types of transitions, internal, calls, and returns, are treated the same. Note that we can have transitions with the appropriately tagged symbols, open parentheses for calls and close parentheses for returns, but there's no automata stack to manipulate, so we won't be able to ensure matched calls and returns. That is, calling context sensitivity. So here our control flow graph will be context insensitive, and all constraints and the user's query must be definable as finite state automata, that is, regular languages. Now the most notable change here is for our crashing stack encoding. Recall the crashing stack from our example, and the S-VPA encoding looked something like this. Now with finite state automata, we can't express matching call and return sequences. So we just replaced each of these well-matched regions with any execution whatsoever. Now this will result in loss of precision for this particular example that I'm using here, because we can't ensure this well-matchedness between calls. So with the encodings for our example for the control flow graph, the user's StackTrace, and query, recall that a precise context-sensitive solver should answer impossible for this query. However, for finite state automata, we weren't able to precisely encode the crashing stack with its well-matchedness, and in fact, a context-insensitive path does exist as shown on the slide, though, as I mentioned, it won't precisely match the crashing stack. So our FSA solver, in this case, would answer possible for this particular query. The final solver also works over the context-insensitive control flow graph and requires that all constraints and the user's query fall under a novel restricted subclass of regular languages, which we call the unreliable trace languages. We call these languages unreliable because they represent sequences of symbols, that is, nodes in our control flow graph, with unknown execution before, between, and after this sequence. So considering traces over the control flow graph, it looks something like at least one instance of the first symbol, followed by at least one instance of the second, and so on. So to give a very brief example, consider the UTL shown here on the slide. If we examine strings that are in versus not in this language, we can see that the point is that there are no constraints on how many times A and B appear in accepted strings, nor what other characters appear in these strings. Only that A and B do appear, and at least once in order. Now for the rest of the talk, I'll actually use vectors of symbols as a convenient shorthand for unreliable trace languages. So the language here is represented by the vector AB. Next, I want to briefly mention how we check intersection emptiness over the context-insensitive control flow graph where the constraints and query are given in UTL. So if we're given a program's control flow graph, the goal is to find a path through this graph where every UTL constraint and the query occur as a subsequence of that path. So for our example inputs, if we convert these to UTL vectors, in this case there is such a path, and again it's precisely the same path we saw for our FSA example. It doesn't precisely match our provided stack trace because we cannot ensure well-matchedness in our stack trace encoding. Now this intersection emptiness check actually only takes time polynomial in the size of the control flow graph and the provided failure report. So I don't have time to go into the details of the algorithm here, but please see our paper for details, or I'm more than happy to chat about it after the talk. Now recall the log message that we had in our failure report. This contains an ambiguous observation. because we don't know for certain which of statement B or C executed. An automata encoding here is straightforward. We just expect to see a B or a C at least some point during accepted executions, while UTL cannot express disjunction, even with loss of precision. So this is a case where UTL lacks the expressiveness in order to encode this particular failure constraint, which would not benefit this solver. Moving on to evaluation, the general strategy was to compare the efficiency and precision of each solver. So for each solver, we're interested in how precisely we can answer queries, how well we can scale to large programs, and how well we can scale from small to large failure reports. Now, we used a diverse suite of applications for evaluation, starting with the smaller Siemens benchmarks, a set of Linux utility programs, and the C compiler GCC. We performed compilation and instrumentation to gather failure reports with the CSI-CC instrumenting compiler, which is built on LLVM. We used the S-VPA lib and OpenFST libraries for our automata solvers. We ran two sets of experiments, first encoding just the failing stack trace for our failure report, and then adding constraints for program coverage data gathered at each call site in the program from CSI-CC. However, before getting to results, I need to talk a bit about how we're going to measure our precision and which queries we're going to use. Now, we used a batch analysis to thoroughly test the scalability of the system. This analysis takes a control flow graph and a failure report and produces partial coverage information. Because remember, we won't expect the failure report to provide complete data on the failing execution. Thus, it partitions the program statements into those that executed, those that didn't execute, and those that might have executed. Hence, for the sets yes, no, and maybe, we can always safely answer that all control flow graph nodes are maybe, but our answer is closer to optimal and more useful to a developer the more nodes we can classify as yes or no. We do this by asking two program coverage queries for each basic block in the program, might block N have executed and might it not have executed, and then based on the answers to these queries, we can classify each into the appropriate yes, no, or maybe bucket. We first measured the percentage of analysis runs for each application that completed versus those that ran out of either time or memory using our analysis. We used a time limit of 3 hours and a memory limit of 32 gigabytes for each analysis run. The first analyses, as stated earlier, use only the stack trace as the lone failure constraint. An analysis that runs out of time completes at least one user query, but could not complete all of them for every basic block in under 3 hours. The main takeaway here is that the S-VPA solver can solve many of the smaller examples, but runs out of time, and this is especially for the larger applications in our test suite. Both the FSA and UTL solvers run out of time only for GCC, which is our largest test subject. However, both take only seconds to answer each individual query, and there are over 100,000 basic blocks in GCC. So practically speaking, they both do quite well here, especially in an interactive scenario where a developer might be asking questions while debugging. Next, we looked at the precision of our analyses, comparing how many blocks it was able to categorize as yes or no rather than maybe. Hence, here, higher numbers are better. It's clear here that the S-VPA solver can be substantially more precise when it completes analysis. However, all numbers in this plot are really quite small, which motivates the use of more dense failure report data. So we brought in this program coverage data encoded as program coverage as I described earlier. So again, looking at analyses that completed versus those that didn't, the biggest message here is that both automata-based solvers have a lot of trouble with memory with large failure reports. While UTL again can solve almost every failure except for GCC, where it solves queries in a few seconds each. And this is extremely impressive because GCC's failure report contains over 13,000 call coverage bits, and hence any solver would need to encode 13,000 constraints to answer even one query. Finally, looking at precision using these full failure reports, note that results here only include those runs that finished, so a lot of bars are missing. Again, S-VPA is significantly more precise where it completes analysis, but perhaps the most impressive story is that the less precise solvers can get substantially better results because they can incorporate more dense failure report data, even though they give up some precision. So to take just one example, the print tokens application disambiguates 20% of basic blocks using the very precise S-VPA solver, but encoding only the crashing stack. While encoding the full failure report with the less precise solver gives us 63% of the basic blocks. Wrapping up, to briefly summarize results, the S-VPA solver had trouble scaling to large programs, while both automata-based solvers had trouble scaling to large failure reports. The UTL solver was remarkably efficient, even with very large failure reports, but it did give up some expressiveness and precision for this efficiency. Thank you all very much for your attention. I'm happy to take any questions. So the UTL solver we wrote from scratch. It's written in Python, as is the analysis infrastructure. The OpenFST solver is written in C, and the S-VPA solver is written in Java. So there's a lot of cross-language going on for the solvers.
Do you think the choice of language may be affecting results?
It's possible. I mean, so when we're talking about memory issues, I think probably less so. I mean, in the case of running out of memory with the automata solvers, it really is just the automata grow so large, I don't think it would make a large difference which language you use for those. That's my sort of subjective opinion.
So I have a quick question. So
Yeah.
is StackTrace the most common form of reports that you get back, or is there any more information that you could exploit such as predicates?
I will claim that stack traces are probably the most common element contained in post-deployment failure reports, right? I mean, certainly people often consider them the most useful. But yeah, I mean, certainly you could take advantage of any other data. In our particular example, for our particular solvers, we can encode anything that you can encode as control flow. So data flow constraints cannot be directly encoded in this framework, but there might be ways. It sort of depends. It's a future work direction.